In this lecture, in this video, we want to discuss group homomorphisms and subgroup structures. Whenever we learn about a new structure in mathematics, we need to ask ourselves, what are the functions from these objects, from these structures to themselves, that preserve those properties, those structures? And the second thing that we need to ask is, what can we say about substructures, the subsets of this structure that have the same properties? The functions that preserve the main properties of our objects are called homomorphisms. You will learn about rings later, and then you talk about ring homomorphisms. In this course, we talk about group homomorphisms. In the linear algebra course, where the objects of interest are vector spaces, you talked about the functions that preserve the structure of these vector spaces. In that case, we call them linear maps. This is often the case. In topology, you look for the maps that preserve the topological spaces. In geometry, you look for the maps that preserve, depending on the type of geometry that you study, differential forms or differential geometry. In any case, in every kind of setting, you should ask yourselves, what are the maps that preserve the structure of the object that you are working with? In some sense, this homomorphisms, these functions that preserve the structure of the subject and the object that you are working with, can be viewed as a global understanding of your structure. And when you work from inside and you try to understand each piece of this object, and sometimes you try to glue these pieces together, that's more like understanding the substructures of your object. In that case, in the case of groups, we call them subgroups. In the case of vector spaces, we call them subspaces. So these points of view, both of them are crucial, and they help each other, of course. The whole thing is supposed to be a tool for us to get a better understanding of the object that we have in hand. Okay, let's make these things more concrete and give a precise definition, at least in the case of groups. Suppose that I give you two groups. The first one comes with an operation that we denote by dot. The second one comes with an operation that I'm going to denote by a star. Then a function from G to H is called a group homomorphism if it preserves the operation. What does that mean? If for every G1 and G2 inside the domain, f of G1 dot G2 is equal to f of G1 times f of G2 with the operation inside H, f of G1 star f of G2. If I have a function f with this property, we call it a group homomorphism. Now let's define subgroup. Suppose G and dot is a group. I give you a subset K of G. Then we call K a subgroup if K with the same operation dot is a group. So K itself with this operation dot that we have becomes a group. Of course, this implies that for every two elements inside K, when I multiply them, I need to get another element inside K and more. We will find out a good way of understanding whether or not a subset is a subgroup later in this video. Let's start with some examples. Suppose n is an integer that is at least 2, then the congruence map that sends an integer a to its residue class modulo n map let's denote this by C sub n. So C sub n of an integer a is just the square bracket of a sub n, the residue class of a modulo n. We know Z is a group under addition, and it's not a group under multiplication. Think about it. And Z sub n is a group under addition. Again, it's not a group under multiplication. And the claim is that this C sub n is a group homomorphism if I think about Z and Z sub n as additive groups. Okay, let's see why this is the case. What does that mean? It means that we need to show C sub n of a plus b is the same as C sub n of a plus C sub n of b. That means the C sub n preserves this group operation. Now, C sub n of a plus b, by definition, is the residue class of a plus b, modulo n. By the way that we define addition on Z sub n, the residue class of a plus b modulo n is precisely the residue class. This, again, C sub n of a plus b is this summation, this residue class. And then the way that we define addition in Z sub n, when I add the residue class that's represented by a to the residue class which is represented by b, we get the residue class that's represented by a plus b. We show that it's a well-defined operation. That's the addition on the set of integers modulo n. The way that we define C sub n, the first term in the summation is precisely C sub n of a, and the second term is C sub n of b, which means C sub n preserves addition. So it is a group homomorphism. Now again, let's look at a function from z to z. This time, I'm going to negate, send x to negative x, looking at the additive inverse of an element x. Claim is that it is a group homomorphism. Let's see why this is the case. So that means I need to check whether or not f preserves addition, which means I need to check whether or not f of x plus y is the same as f of x plus f of y. Now, f of x plus y, the way that we defined it, is negative of x plus y. We showed that inverse of g times h is inverse of h times inverse of g in general. In the case of integers, actually, we've seen it long ago, maybe in middle school or maybe in elementary school, that negative of x plus y is negative of x plus negative of y, or we can use what I just mentioned from group theory. In either case, we have that this is the same as negative x plus negative y. But that is f of x plus f of y, which means f is indeed an abelian group, a homomorphism. Now let's look at positive real numbers. Now notice that positive real numbers under multiplication is a group. If I multiply two positive real numbers, I end up getting another positive real number. If I start with a positive real number, its inverse is again its multiplicative inverse, 1 over x, is again a positive real number. 1, of course, is a positive real number, which means this set does have a neutral element under multiplication. And multiplication has associativity property. So altogether, we get that it is indeed a group under multiplication. Now think about the natural logarithm map from positive real numbers to the entire real numbers. The set of real numbers itself is a group under addition. And the claim is that this map is a group homomorphism. Again, notice that real numbers under multiplication is not a group because not every element has an inverse. 0 does not have a multiplicative inverse. So R is a group only under addition, and the claim is that this natural logarithm map from the set of positive real numbers to the set of real numbers is a group homomorphism. Let's see why this is the case. Again, what does that mean? I need to check whether or not natural logarithm of x times y is natural logarithm of x, this time plus natural logarithm of y. And I need to use plus here because the group operation of R here is plus. So here, again, we are thinking about R as an additive group, as otherwise it's not a group at all. And we are using this plus over here because the operation inside the real numbers is plus. And we are using multiplication over here because multiplication is the operation of the domain. So we need to check whether or not natural logarithm preserves the operation, the group operation, which means we need to check the equality that we have over here, which is true. Natural log of x times y is equal to natural log of x plus natural log of y, and therefore the natural logarithm is a group homomorphism from the set of positive real numbers to the set of real numbers, to the group of additive real numbers. Now let's think about non-zero complex numbers. Non-zero complex numbers is a group under multiplication. The set of positive real numbers is a group under multiplication, as we just discussed. Now let n be the norm of every complex number, which means the absolute value of this complex number. So let's recall that absolute value of x plus y, x plus iy for real numbers x and y is the absolute value is square root of x squared plus y squared. So intuitively, it is the Euclidean length of the segment that connects 0 to I, 0 to z, when I think about z as a point in the complex plane. Then n is a group homomorphism. And the reason is that what we've learned in calculus about complex numbers, that absolute value of product of two complex numbers is indeed product of absolute values of these complex numbers. And therefore, the way that we define group homomorphisms, we deduce that n is a group homomorphism from non-zero complex numbers to positive real numbers. Remember, absolute value of z is always a positive real number. And if we start with a non-zero complex number. Okay, let's look at the next example. So far, we have been working with abelian groups, meaning groups that we are allowed to switch the order. Now let's look at an example where my group is not necessarily abelian. In fact, most of the time it's not abelian. Let's look at a GLNR. GLNR is the set of invertible n by n real matrices. So GLN, general linear group. It stands for general linear group. So GLNR is the set of invertible n by n real matrices. So this R over here gives us that all the entries should be real numbers. This n tells us that it should be n by n, and saying that it is GL, general linear, tells us that it is supposed to be invertible with the inverse inside the real numbers as well. From linear algebra, you've learned that in fact matrix multiplication is associative. When I multiply A by B, matrix A by another matrix B, and then multiply by another matrix C is the same as multiplying A by B times C. So multiplication is indeed an associative operation. And when I multiply two invertible matrices, their product is also invertible. In fact, this we can also use what we had earlier and realize that B inverse A inverse is an inverse of A times B, because this is going to give us this, and that is identity. And similarly from the other way around. And therefore, product of two invertible matrices is always an invertible matrix. So GLNR under multiplication is a group. This is an important group. We study this group and all the subgroups of this group in a subject as a part of a group theory, which is called linear groups. So a study of linear groups is an important part of group theory, and it helps us to understand other parts of mathematics as well. It is important for understanding topological spaces or hyperbolic spaces and so on. Now, let's think about GLNR. Now, the following function from GLNR to itself, let's call it theta, is a group homomorphism. What is theta? Theta takes a matrix, looks at its transpose, and takes its inverse, its multiplicative inverse. Now, x sub t is the transpose of x. Claim is that this theta is a group homomorphism. Okay, let's see. I need to check whether or not theta of x dot y is theta of x times theta of y. I see that theta of x times y is x times y transpose and then inverse. But when I look at transpose of x times y, it's similar to, it is equal to transpose of y times transpose of x. It flips the order of multiplication. And then I need to look at the inverse of this. And that is the same as inverse of the second matrix times inverse of the first matrix. So x transpose inverse times y transpose inverse. And from here, we deduce that it is theta of x times theta of y. Of course, I need to justify as well why theta is well defined, in a sense that I need to say why theta of x is invertible, or why x transpose is invertible. And notice that x times x inverse, if I look at transpose of both sides, I get that it is the same as x inverse transpose times x transpose. And similarly, this is identity, and this is the same as x transpose dot x inverse dot x transpose, the whole thing transpose. From here, we deduce that x transpose is invertible, and moreover, x transpose inverse is the same as x inverse transpose. So it doesn't matter what order I pick, therefore theta is indeed invertible, and not theta of x is invertible, and it's a well-defined function. Now, the next example shows us, gives us a kind of restriction. So it's an exercise for us. It's an abstract exercise for us to work with group homomorphisms and see what kind of properties we can detect for the group if I'm given certain group homomorphism. Now, in the case of ring of integers, we've seen that if I send x to its additive inverse, it's going to be a group homomorphism. Next, we are going to show that this phenomena happens only for abelian groups. So suppose G is a group under multiplication under the operation dot, and I give you a function f which sends every element to its multiplicative inverse. Claim is that this function is a group homomorphism precisely when group G is abelian. And recall that abelian means that the order of multiplication doesn't matter for every pair of elements from the group. So I start with the assumption that F is a group homomorphism, and I want to show that that G is abelian. But let's recall what it means for F to be a group homomorphism. F being a group homomorphism means f of G dot H is the same as f of G dot f of H for every pair of elements G and H inside G, the group capital G. Now, by definition, f of G dot H is G dot H inverse, and f of G is G inverse, and f of H is H inverse. From this equation, knowing that F is a group homomorphism, we deduce that G dot H inverse is G inverse times H inverse. We have proved that G dot H inverse is inverse of the second term times inverse of the first term, is H inverse times G inverse. So this product is supposed to be the same as G inverse times H inverse. Now, it seems that we are done, because at least we know all the inverses are commuting with each other. So let's call G to be, okay, so you give me a pair. I want to show that X and Y commute. I plug in, instead of G, I am going to plug in inverse of X. And instead of H, I'm going to plug in inverse of Y. I'm going to plug in inverse of X for H and inverse of Y for G inside this equation. Then the left-hand side is inverse of Y inverse times inverse of X inverse, and the right-hand side is inverse of X inverse times inverse of Y inverse. But notice, we showed that inverse inverse gives us back the element that we started with. So X inverse inverse is just X, and Y inverse inverse is simply Y. So from this equality, we deduce that X times Y, Y times X is equal to X times Y, and that means that group G is abelian. Now, let's assume that G is abelian, like the the group of integers under addition, and I want to show that sending G to its inverse is a group homomorphism. Okay, so F sends G dot H to G dot H inverse, but that means it is, because we know inverse of product is inverse of the second one times inverse of the first one. Inverse of H is f of H, inverse of G is f of G. But my group is abelian. That means I'm allowed to flip the order of multiplication. Therefore, that is f of G times f of H, and that's exactly what we wanted to show. We ended up getting that f of G times H is f of G times f of H when the group is abelian. So that completes proof of this example. So this example provides us an important collection of group homomorphisms. We come back to this example later when we talk about group automorphisms. So suppose I give you a group G under multiplication, and this operation most likely is not commutative. The group is not abelian. So this example is interesting and exciting when the group is not abelian. Of course, it is okay if the group is abelian, but in that case, the example will not be an interesting example. It will be just identity map. Now, what is the example? I give you this group and I give you an element small g inside this group. Now I can define this function from G to G. So what is the function? I feed it an element of the group. It multiplies this element by G on the left and G inverse on the right. We say we have conjugated X by G. So this is a conjugate of x. So it's a conjugate. We have conjugated x by g. So this is called a conjugate. So let's write it over here. A conjugate of x. Okay, but for this example, this name is not important. What is important is to remember that given g, I can multiply every element by g from left and its inverse from right, and that's an interesting function to remember. And claim is that this function is a group homomorphism. So please remember this group homomorphism, and the name is important for us when we want to recall this group homomorphism. So we are conjugating x by g. Okay, so claim is that conjugation by g is a group homomorphism. What does that mean? That means I need to show that when I conjugate x times y by g, that's product of conjugating x by g and conjugating y by g. And the order doesn't change, it stays the same. If it is x times y, then conjugation of x, then conjugation of y. Okay, let's write them down. The left-hand side is g dot the element that I have here, x dot y, and then inverse of g. And notice that I did not put parentheses because multiplication is associative, so it is okay to avoid writing parentheses. Now let's look at the right-hand side. I have conjugation of x by g times conjugation of y by g. So let's write it down. This is the conjugate of x by g, and then I'm multiplying it by conjugate of y by g. Then I can drop the parentheses, or I can emphasize that I'm going to focus on multiplication of these two terms, and notice that they cancel each other out. G inverse dot g is just the neutral element, and neutral element by definition it can be avoided, is a neutral element in multiplication, so I can drop it out. It doesn't change anything. So altogether I end up getting that it is what we expected. It is conjugation of x dot y by g, and that gives us the equality that we desire, that c sub g of x dot y is product of c sub g of x and c sub g of y. Okay, so we learned about c sub g, and we saw that this is a group homomorphism. Next is another important example. It gives us a group homomorphism from Z to any other group. So you give me a group, you pick your favorite element from this group, let's call it G. So it's a fixed element, you fix this element. And then you raise it to power n, as n ranges in the set of integers. And this function that sends n to G to power n is a group homomorphism. So it's kind of similar to exponential function, right? So let's see, what do I mean? Here the operation is addition. Here the operation is denoted by dot or multiplication. Then I need to show that f of m plus n is f of m times f of n. This is what I need to show in order to deduce that f is a group homomorphism. By definition, f of m plus n is g to power m plus n. F of m is g to power m, f of n is g to power n. And we had shown this, that g to the m times g to the n is equal to g to power n plus n. If you remember, we looked at many different cases depending on positivity or negativity of m and n to show that g to power n plus n is equal to g to the n times g to the n, from which we immediately deduce that the function f, which sends n to g to the n, is a group homomorphism. So far, we have discussed group homomorphisms, and we saw many examples for group homomorphisms. Next, we want to see some examples for subgroups. So let's start with basic examples coming from numbers. Rational numbers and addition forms a group, and a set of integers is a subset. And of course, Zn plus is a group as well, as we've seen before. Therefore, Z is a subgroup of Q and addition. The set of real numbers and addition form a group, and Q is a subgroup. Q is a subset of real numbers, and Qn plus forms a group, and therefore Q is a subgroup of real numbers and their addition. Similarly, complex numbers and addition forms a group, and real numbers is a subset of complex numbers which forms a group under addition. Therefore, this is also a subgroup. Now, do we have any subgroup inside Z? There are many subgroups inside Z. For instance, the set of even numbers, it's closed under addition, inverse of an even number, and an additive inverse of an even number is also even. And it is a subgroup. You can simply check it. Let's actually do it and make sure that you understand why it is a subgroup. The claim is that it's a subgroup under addition. It should be closed under addition. Otherwise, plus does not give us an operation on this set. I pick two even numbers, 2k and 2l. These are an arbitrary even numbers. I add them. I can see that it is still a multiple of 2. It is still an even number. So plus does give us an operation on the set of even numbers. Plus is associative. 0, which is 2 times 0, is an even number. It is inside the set of even numbers, multiples of 2. For every even number, x plus 0 is the same as 0 plus x, and it is x. So we do have neutral element with respect to addition inside the set of even numbers. Every even number that I give you, its inverse, its additive inverse, is still an even number, and therefore, and when I add it, by definition, I get the neutral element 0. And so I have all the properties of being a group. Therefore, 2Z is a subgroup of Z and addition. Now, let's see a non-example. The set of non-zero real numbers is a subset of real numbers, but it is not a subgroup of real numbers under addition. Real numbers and addition forms a group, but the set of non-zero real numbers is not a subgroup of real numbers under addition. Why is that the case? Because it's not closed under addition. If I give you 1 and -1, when I add them, I end up getting something that is not inside this set. 1 and -1 are here, but when I add them, it's not here. That means addition does not even give us an operation on this set. Therefore, it's not going to be a subgroup of Rn plus. Remember, the set of non-zero real numbers and multiplication is a group. But being a group under multiplication does not tell us, is not true, it does not imply that it's a subgroup of R under addition. I'm not allowed to change the operation of the group that we are given and claim that I am a subgroup. Now let's see two general examples of subgroups. If I give you an arbitrary group, the set that contains only one element, and that's the neutral element of G, is definitely a subgroup of G. The other one is the entire group. The entire group is, of course, clear that it is a group under multiplication. How about the set that has only neutral element in it? So I need to check whether or not it is closed under multiplication, but it is the case because neutral element times itself is the neutral element. And because of this, we can also deduce that its inverse is the same as itself under multiplication. And now associativity is, of course, clear because I have only one element here. And we have also inverse. That's it. So it implies that the set that contains only one element, which is neutral element, is a subgroup of G. Now, if I think about this example to Z being a subgroup, there are a few parts that seems to be redundant. So for instance, this part that plus is associative, of course it is, because otherwise Z and plus would not be a group. Because Z and addition is a group, of course I know plus is associative. I shouldn't be forced to repeat this. The other thing is this finding inverse. I don't need to check this again if I know that my set is closed under finding inverse. So if I know that my set is closed under finding inverse and it is closed under my operation, whatever it is, I automatically deduce that also the neutral element is there. So it seems that some parts are redundant, and the question is, can I make it in a more compact form, find a criterion that's a compact form of checking whether or not a subset, a non-empty subset, is a subgroup. Okay, so that brings us to so-called subgroup criteria. I'm going to present the most compact form of a subgroup criterion. There are two steps criterion as well, but here I'm presenting only one step criterion. Suppose a G is a group under multiplication under the operation dot, and now I give you a subset H of this group. I tell you that it is not empty, and I tell you that if you give me a pair of elements inside H, then X dot inverse of Y should be inside H as well. And when we use the additive notation instead of dot, then we need to write it X minus Y instead of X times Y inverse. Just a remark. So if I have this property, then H is a subgroup. And we call this a subgroup criterion. Okay, let's try to prove this. I need to check that H and dot forms a group. In particular, I have to show that H and dot is, I need to show that dot gives me an operation on H, which means H is closed under multiplication. If I give you two elements inside H, when I multiply them, look at x dot y, why am I still inside H? To show this, we start with showing y inverse of every element inside H is still inside H. Okay, so let's see why this is the case. Suppose, in fact, before this, we show that the neutral element is inside H. So in particular, this argument shows even more about subgroups, about sets that have this property that X dot in Y inverse is inside H. Okay, so let's go back, repeat what I want to say. I'm going to assume that my set is non-empty. I'm going to assume that if I give you a pair of elements inside this set, X times Y inverse is inside H. I want to show that H is a subgroup. Before showing that dot defines an operation on H, I'm going to show two things. First, I'm going to discuss why the neutral element of G is inside H. Then I'm going to discuss why inverse of every element of H is inside H. Then I'm going to use these facts to deduce that x dot y is inside H if x and y are in H. Okay, let's start with the neutral element. We know that H is not empty. That means I have some element inside H, let's call it x naught. I'm going to use the hypothesis that if x, y belong to H, x comma y belong to H, then x dot y inverse is inside H. I'm going to apply this for the pair of elements x naught, x naught. Because x naught is inside H, I deduce that x naught times x naught inverse is inside H. That means the neutral element is inside H. So that's the first claim that I have made. Next, I'm going to show that inverse of every element of H is still inside H. So I give you an element inside H. I know that neutral element is inside H. I'm going to use this. I'm going to plug in neutral element for X and Y for Y. What do I get? I get that neutral element times inverse of Y is inside H. Neutral element being the neutral element give us that Y inverse is inside H. Okay. Now I give you X and Y inside H. I want to show that dot is an operation on H, which means I need to show that H is closed under multiplication. I give you a pair of elements, X and Y inside H. I want to deduce that X dot Y is inside H. Here I have that X dot Y inverse is inside H. So I need to change this to Y. So I need to use the same thing, but not for the pair X and Y, but rather for the pair X and Y inverse. But I have to point out why Y inverse is actually inside H, and that we have proved in here. Because of this statement, because of this, and knowing that Y belongs to H, we deduce that Y inverse is also inside H. Now, X and Y inverse are inside H, imply that, so knowing that X and Y inverse both of them are inside H, we can deduce that X dot inverse of Y inverse is inside H. And inverse inverse is the element itself. So that implies that instead of this, I can write Y. Therefore, X dot Y is inside H. So this discussion implies that dot defines an operation on H. We do have the neutral element inside H, and we do have inverse of every element inside H, and dot is definitely associative because G and dot forms a group. All together, we have all the properties of being a group under dot. So this is associative. H does have the neutral element of this operation, and every element of H has an inverse with respect to this operation inside H. So altogether, we get that H and dot form a group, and therefore H is a subgroup of G. So we proved the subgroup criterion. In order to show a non-empty subset of a group is a subgroup, it's enough to show that X dot Y inverse is inside H for every pair of elements X and Y in H. Now, let us make two important remarks about subgroups in general. So here in this proof, we've seen that if I satisfy this condition, then neutral elements are inside H. Next, we are going to show that this property is also true for every group. In fact, what we are going to show is a kind of converse of the subgroup criterion. we are going to show that if I start with a subgroup, then for every pair x and y inside the subgroup, x dot y inverse is inside H, the neutral element is inside H, x dot y is inside H, and these type of things. X dot y is of course clear, but so these are the statements that we are going to discuss. So suppose H is a subgroup, then the claim is that the neutral element of the group is inside H, and every pair of elements that I give you, x dot y inverse, is inside H. So it's the converse of subgroup criteria with this additional information. Okay, because H is a subgroup, H is non-empty set, and it has a neutral element, in fact. So suppose the neutral element of H is E sub H. Being a neutral element for the operation dot, we deduce that E sub H times E sub H is equal to itself, because it's a neutral element under multiplication. But if you remember, we have cancellation law in groups. So I can cancel out these two in the group G. When I cancel this guy out in the group G, I end up getting the neutral element of G on the right-hand side. When I cancel out this guy, I end up getting the neutral element of H in the right-hand side. So in the right-hand side, only I get neutral element of H. In the left-hand side, I end up getting the neutral element of G. Therefore, the neutral element of a subgroup is the same as the neutral element of the group, and therefore E sub G belongs to H. To make this cancellation property and this step more clear, let's redo the proof of cancellation law, and that means we essentially multiply both sides of this equation 1 by inverse of E sub H. So let's multiply from right or left, doesn't matter. Let's multiply it from right. So when I multiply from right, again, use associativity, I notice that this product is the neutral element of the group G, and this product is the neutral element of the group G, but neutral element times E sub G doesn't change it, E sub H doesn't change it, so I get that E sub H is equal to E sub G. And therefore, E sub G belongs to the group, to the subgroup H. So every subgroup contains the neutral element of the group G. Now, because H is a subgroup, under it is closed, it has, every element has a multiplicative inverse. Okay, so every element of H has an inverse in H. So if I give you y inside H, then I can find y prime inside H, so that y times y prime is the neutral element of the group H, and y prime times y is the neutral element of the group H. But we have just proved that neutral element of H is the same as neutral element of G. So that means y times y prime is equal to the neutral element of the group G. But that means y prime is inverse of y. I can simply multiply both sides of this by inverse of y and deduce that, okay, inverse of y, this cancels out, I get the neutral element, therefore y prime is inverse of y. So we deduce that inverse of y is inside H. Remember, y prime is inside H. So inverse of every element of H is still inside H. And because H is closed under multiplication, if I give you a pair of elements x and y inverse is inside H, then x and y inverse, both of them are inside H, and therefore their product is inside H. So we proved the converse of subgroup criterion as well. Now let's try to use this to see some examples. For instance, in the set of integers, in the group of additive integers, in the group of integers under addition, all multiples of a given integer n form a subgroup. So for every n inside Z, the set of multiples of n is denoted by nz. That's the set of multiples, integer multiples of n, that forms a subgroup of Z. Let's see why it's a subgroup of Z. I need to check that it is not empty. Then I need to check that if x and y belongs to this set, then, because I'm using addition, instead of writing x dot y inverse, I have to say x minus y is inside this set. So let's start with why it is not empty. So it's of course not empty because every multiple of n is here. In particular, 0, which is n times 0, which is a multiple of n, is inside this set. So it is not empty. That's good. I give you two elements inside this set. So x and y are multiples of n. That means x is n times k, y is n times l for some integers k and l. Then I look at x minus y. That is nk minus nl. I can factor out n, and I get that it is n times k minus l. Remember, k minus l is an integer because both k and l are integers. That means x minus y is an integer multiple of n, and that means that it is inside nz. Therefore, by the subgroup criterion, nz is a subgroup of the set of integers under addition. Now let's try to understand centralizer of an element. What does that mean? I give you a group G with an operation dot. I give you an element, small g of this. I'm fixing this small g. I'm not changing it. So maybe it's better to put the dot over here, not so g not. So g not. I'm fixing this element. Then I have to also put a not over here. I'm fixing this element, and I'm asking myself, what elements of the group G commute with G naught? That means G naught dot x is the same as x dot G naught. I'm allowed to flip the order of multiplication. What are those elements? I put them all in a set. I call that set the centralizer of G naught. So the centralizer of G naught consists of all the elements that commute with G naught. Claim is that this guy is a subgroup of G. Okay, let's try to prove this. I have to change all these G's to G naught because I want to emphasize that this is not an arbitrary element of the group, but rather a fixed element. We fixed it at the beginning of the whole discussion, and we are going through these arguments. So I'm going to change as much as I can and then start going through the proof that I have written over here. Okay, let's try to understand the argument. Again, we have a subset of the group G. I want to use the subgroup criterion in order to show that the centralizer of G naught is a subgroup of G. And that means I start with proving that this is a non-empty set. Next, I will discuss that if x and y are in this set, then x dot y inverse is inside this set. To show that x dot y inverse is inside this set, sometimes we first discuss what happens to y inverse, then bring in x into the play. But let's start with arguing why it is not empty. Often, it is useful to think about the neutral element when we want to show a certain set is not empty in order to prove that it's a subgroup. Remember, if I give you a subgroup, it needs to contain the neutral element. So it's not a bad idea to discuss what happens to neutral element. Maybe it's easy to show that neutral element belongs to this set. In particular, this set is not empty. In the case of centralizer, we use this idea as well. I want to show that centralizer of an element is never empty. I'm going to look at the neutral element and notice that neutral element times every element doesn't change it, no matter if I multiply it from left or right. So the neutral element indeed commutes with the element G0, and so it does belong to the centralizer of G0. In particular, the centralizer of G0 is never empty. Now, I give you two elements, both of them in the centralizer of G0. I want to use the subgroup criterion and show that x dot y inverse is inside the centralizer of G0. That's my goal. So we want to show that x times y inverse is inside the centralizer of G0. But let's recall what it means for x and y being inside the centralizer. X is in the centralizer precisely when it commutes with G0, which means x times G0 is supposed to be the same as G0 times x dot x. Similarly, y being in the centralizer of G0 means y dot G0 is equal to G0 dot y. Okay. I have to use these 1 and 2 to deduce this equality. I need to bring y inverse to the picture. What do I know about y? I know that y dot G0 is the same as G0 dot y. I want to bring y inverse to the picture. Let's multiply both sides of this equality by y inverse from right, from left, and from right. I want to get rid of both of these y's as well and bring y inverse. When I multiply, when I do as I said, so I'm looking at this equality, multiplying both sides of this equality by y inverse from right and left, I end up getting this equality. So this is equal to this one. I'm taking this equality and multiply both sides of this by y inverse from both sides. Now I reorder the terms. This cancels out this one. I end up getting G0 times y inverse. And this y cancels out this one. I end up getting y inverse times G0. So this equality implies what? Let's think about it. Let's read it out loud. It's G0 dot y inverse equal to y inverse dot G0. Now let's think about it. This means G0 and y inverse commute, which means y inverse is in the centralizer. But I want to show that x dot y inverse is inside the centralizer. So I need to write down x dot y inverse and see if I can commute it with G0. I use associativity and deal with one commuting at a time. We know that I can commute y inverse and G0, so I do that. Using associativity, I drop these decorations, parentheses. Now I commute x and G0 because I know that I can commute them because x is in the centralizer. Altogether, I end up bringing G0 all the way to the left, and I get that it is G0 times x dot y inverse. So we started with having G0 on the right of this term and bringing it to the left of this term, and therefore x dot y inverse is in the centralizer, which implies that it is indeed the subgroup criterion actually holds, the condition of subgroup criterion holds, and therefore by the subgroup criterion, centralizer of an element G0 is a subgroup of the group capital G. Next, we define the center of a group. So I give you a group G, let's say with operation dot. Then the center of the group means all the elements of the group that commute with every element of the group. So in the centralizer, I'm fixing G naught and I'm asking what are the elements that commute with this G naught. In the center, I pick an arbitrary element of the group and I still need to commute with it. So X needs to commute with for all G inside the group. For all G inside the group, we need to have G dot X equal to X dot G. The collection of such elements is called the center of G, and we denote it by Z of G. Claim is that this is a subgroup. Okay, so again, I want to use the subgroup criterion. I want to show that it is not empty. As I mentioned in the previous example, we looked at the neutral element. That would be a good starting point to show that it is not empty. So I need to discuss why the neutral element is in the center of G. What does that mean? That means I need to check whether or not this equality is true for every G inside the group. But notice G dot, the neutral element, is G, no matter if I put G on the right or left, right of the neutral element. In either case, we end up getting G. That means I can switch the order of the neutral element dot every other element. Therefore, the neutral element belongs to the center of the group G. And that's exactly what we wanted to show. So we have the first part, that the center of the G is always not empty. Next, I want to argue that we have the main part of the subgroup criterion, meaning if X and Y are a pair of elements inside the center, then X dot Y inverse is still inside the center. So again, I need to bring Y inverse to the picture. But what does that mean that Y is inside the center? Y being inside the center means for every G inside the group, YG is GY. Now, that means for every G, Y is in the centralizer of G. But centralizer of G is a subgroup that we have proved. Okay, actually, in this way, I'm giving you a more a faster route to the proof of this. We can do it in a slower way. I'll tell you later. We have proved that this is a subgroup for every G. We know that X commutes with G because of this, and Y commutes with G because of this. So X and Y, both of them are inside the centralizer of this G. Now, centralizer of G is a subgroup, and therefore X, Y inverse is inside the centralizer of G, no matter what G I pick. That means X, Y inverse dot G is G dot X, Y inverse for every G, for all G inside the group, from which we can deduce that X dot Y inverse is inside the center of G. Therefore, we can use the subcriterion. Of course, I could repeat the proof that I had earlier, and each time emphasize that the implication is true for every G. So I could have written over here that YG, GY, multiply both sides by Y inverse from left and right, and deduce that I can multiply both sides by Y inverse from left and right, cancel out the unneeded letters, and then end up getting that it is Y inverse that commutes with G. and then use this and show that x dot y inverse dot g is the same as g dot x y inverse, as we did in the previous example. But the whole point is that the whole thing is true for all g inside the group, and therefore we get the implication. That's an alternative way of arguing. But the reason that I mentioned it the way that I did using centralizer is the following remark, that center of G means that we are in the centralizer of every element of the group. So an element X is in the center if and only if it is in the centralizer of every element inside the group. So center can be viewed as intersection of all the centralizer subgroups. Therefore, the next example that we have can give us an alternative way of proving that center is a subgroup. So the next example tells us that if I give you a family, a collection of subgroups, their intersection is always a subgroup. So intersection of finitely many, infinitely many, doesn't matter. If you give me a bunch of subgroups, then when you intersect them, you are going to get another subgroup. So here I'm collecting them using this index notation. So I is changing in certain index set. This capital I can be an arbitrary set. I'm giving you a collection of subgroups of the group G under multiplication. Then claim is that when I intersect them, I'm going to get another subgroup of the group G. Okay? This is what we have kind of used. We didn't use it, but we could use and give an alternative proof for center of a group being a subgroup. We use this intersection property in order to define the so-called subgroup generated by a set, the smallest subgroup that contains a given set. It's an important example to have in mind. So let's define, let intersection of the whole H sub i's be denoted by H. Because H sub I is a subgroup, by the result that we proved where we showed the converse of subgroup criterion, we also showed that the neutral element of G is always inside every given subgroup. In particular, E sub G belongs to H sub i's, no matter what I pick. And therefore, E sub G is in the intersection of all H sub i's, which means it is inside H, and therefore H is not empty. So again, I'm trying to use the subgroup criterion in order to show that H is a subgroup. Here, using this technique, we deduce that H is not empty. Next, I want to show that if X and Y are inside H, then so is X dot Y inverse. Okay, what does that mean and how we can achieve it? When X and Y are inside H, that means that they belong to the intersection of H sub i's, which means no matter what index I pick, both X and Y are inside H sub I. H sub I is a subgroup. So by the converse of the subgroup criterion, we know that when X and Y are inside H sub I, so is X times Y inverse. But this is true for every index I. So X dot Y inverse is in every H sub i's, which means it is in the intersection of all H sub i's. So X dot Y inverse is inside H, as we wanted to show. Therefore, by the subgroup criterion, this intersection is a subgroup, and that's exactly what we wanted to show. Now, next what I want to do, so we have discussed group homomorphisms, and we've seen some of the basic examples of group homomorphisms. Then we saw We define subgroups. We discuss some examples. We've seen some properties like subgroup criterion, converse of subgroup criterion, intersection of a family of subgroups, centralizer subgroups, center of a group. So we saw these general examples of subgroups and their properties as well. Now, next, what we want to do and we want to explore is the connection between group homomorphisms and subgroups. If you remember, in linear algebra, we've seen that if I give you a linear transformation, its kernel is still a subspace and its image is also a subspace. We show the same type of properties for group homomorphisms. So when I give you a group homomorphism from a group G with operation dot, another group H with operation star, then the image of F, the range of F, is denoted by IMF. That is the notation that we are going to use in this class. That's the image of F. That is a subset of codomain. And the kernel of F, so image of F is simply the set of all the values that F takes as G ranges inside the domain. And the kernel of F, similar to linear algebra, is the set of all the elements of the domain that are killed, that are mapped to the neutral element. In the linear algebra setting, the neutral element is 0. So everything is sent to 0. Here, a neutral element, it depends on the group operation. So let's denote it by E sub H. That's the neutral element of my codomain H. Now, we defined image and kernel. Next theorem tells us that if I start with any group homomorphism, its image is a subgroup of the codomain H, and its kernel is a subgroup of the domain of F. So starting with any group homomorphism, we get two interesting subgroups. One of them is image, that's a subgroup of codomain, and the other one is kernel, that's a subgroup of domain. So in order to prove this theorem, I need to review or check or show some basic properties of group homomorphisms. What do we know about group homomorphisms? So far, we just know by definition that they preserve group operations. But in a group, we have kind of two other operations as well. One of them is a constant operation, that is the neutral element. The other one is is not a binary, is a single operation which sends x to x inverse. We have only discussed the binary operation of multiplication for groups, and we define group homomorphisms only in terms of this binary operation. How about the other operations, the neutral element and inverse? And that's the content of the next proposition, which says that a group homomorphism, the way that we define it, indeed preserves the other properties as well. It does send the neutral element of the domain to the neutral element of the codomain, and it does send inverse of an element of the domain to inverse of f of g. Okay, so these are the content of this proposition. So essentially, a group homomorphism does preserve this constant operation, the neutral element, and the sending G to G inverse. So here again, the point is that f of G inverse is the inverse of f of G inside the codomain, and G inverse is the inverse of G inside the domain. So I'm allowed to switch the order of taking these operations, sending an element to its inverse or applying F. Let's start with part one. Why is the neutral element sent to the neutral element of the codomain? Because E sub G is the neutral element of G, I do know that E sub G squared is E sub G. E sub g times E sub g is E sub g. Then I'm going to apply my group homomorphism to both sides of this equation. Because F is a group homomorphism, it preserves the dot multiplication. And I deduce that F of E sub g dot E sub g is the same as F of E sub g dot F of E sub g. Now I notice that is E sub g times E sub g. Now I'm going to use this equality. And I know that F of E sub g times E sub g is F of E sub g. So this side is F of E sub g, and this side, I write it as it is. So I get this equality. Now I cancel out these two. That means I'm going to multiply both sides, or I can write down this as F sub g times the neutral element of the codomain and use the cancellation law. Essentially, I'm canceling out, as I mentioned. I'm going to cancel out these two. I deduce that F of E sub g is nothing but E sub h, which means the neutral element of G is sent to the neutral element of H under a group homomorphism F. Now let's see why inverse of an element is sent to, so F of G inverse is F of G inverse. So in order to show that, we start with what it means to be G inverse. That means that G times G inverse is the neutral element of the group. Now I'm going to apply my group homomorphism to both sides. I deduce that F of G times G inverse is F of the neutral element of G. But remember, in part 1 we showed F of neutral element of G is equal to the neutral element of H. And because F is a group homomorphism, this is F of G times F of G inverse. So altogether we get that F of G times F of G inverse is equal to the neutral element of H. Now I can multiply both sides by inverse of this. And I deduce, okay, so these guys cancel out. I deduce that F of G inverse is F of G inverse. Okay, of course, this is the neutral element. It doesn't matter. I get the desired equality. So a group homomorphism F sends the neutral element of domain to the neutral element of the codomain. And F of G inverse is F of G inverse. I'm allowed to switch the order of taking inverse or applying F when F is a group homomorphism. Now we are ready to show that image of F and kernel of F, both of them are subgroups. Let's go to the proof of that theorem. Let's say I want to show image of F is a subgroup. Again, I'm going to use subgroup criterion, and that means I need to show why it is not empty. Notice that F of the neutral element is definitely inside the image, and therefore it belongs to the image of F. And remember, this is the neutral element of H, but I don't use it now. So this implies that the image of F is not empty. Next, I want to show the main property of being the main property in the subgroup criterion, which means I pick a pair of elements inside the image. I need to show that the first one times inverse of the next one is still inside the image. Let's call these elements X bar and Y bar. Because both of them are in the image, X bar is F of something and Y bar is F of something, where X and Y, these somethings belong to the domain G. Now I'm interested in the first one, my group operation inverse of the next one, and I need to show that this belongs to the image. So let's do some game, let's play with this side. We know that Y, by definition, X bar, the way that we showed, because X bar and Y bar belongs to the image, we know that X bar is F of X and Y bar is F of Y for some X and Y inside the group. So this is f of y inverse, but we proved that f of y inverse is the same as f of y inverse. I can switch this order. I get that f of x times f of y inverse. Now f is a group homomorphism. So that means f preserves multiplication. So f of x star f of y inverse is nothing but f of x dot y inverse. All of a sudden we deduce that this element itself is f of something, and therefore it is in the image of f. So image of f is a subgroup using subgroup criterion. Is a subgroup of the codomain using subgroup criterion. Now let's see why kernel is a subgroup. Again, I want to show kernel of f is not empty. We have already discussed that f of the neutral element is the neutral element of the codomain, which means the neutral element of G is sent to the neutral element of H. By definition, that means E sub G belongs to the kernel of f. Remember, kernel of f traces all the elements, gives us all the elements that are sent to the neutral element of the codomain E sub H. Now, suppose x and y are in the kernel. I need to show x times y inverse is inside the kernel. Okay, we need to show this. But let's, before that, make sure that we understand what this means. This means f of x is the neutral element of the codomain, and f of y is also the neutral element of the codomain. These are our hypotheses. Now we want to show that x dot y inverse is inside the kernel of f, and that means I need to discuss why this equality is true. So I need to compute f of x dot y inverse. So that's what we are doing. We know f is a group homomorphism. That means f of product is f of the first one star f of the next one. F is a group homomorphism, so f of y inverse is f of y inverse. So I can replace this by f of y inverse. So this one I didn't touch. Because x is inside the kernel, I have this equality. So I write E sub h instead of this one. And because y is inside the kernel, I have this equality. And instead of y, I'm going to write down the neutral element of h. Inverse of a neutral element is itself. So altogether, I read that it is still the neutral element of h. So f of x times y inverse is the neutral element of h. And that's exactly the equality that we needed to deduce that this is inside kernel of f. Therefore, by the subgroup criterion, kernel of f is a subgroup of the domain. Now let's see some examples of image and kernel. Let's look at some of the examples that we have as for group homomorphisms. So C sub n from Z to Z sub n, which sent an integer a to the residue class of a modulo n. Every Z sub n, every element of integers modulo n is the residue class of some integer. That means every element of the codomain is in the image of C sub n. And therefore, image of C sub n is the entire Z sub n. Okay, so that tells us image. Now let's look at the kernel. Now, an element is inside the kernel if and only if it is sent to the neutral element of the codomain. That means an integer a is in the kernel when C sub n of a is the residue class of 0. Now, C sub n of a is the residue class of 0 if and only if the residue class of a is the residue class of 0, and that is the case when a and 0 are congruent modulo n. That means a is a multiple of n and vice versa, as in is an integer multiple of n. So that altogether we deduce that the kernel of the residue map modulo n is nothing but integer multiples of n. Now let's look at the other example that we had, the norm map from non-zero complex numbers to positive real numbers under multiplication. What is kernel and image of this map? Let's start with image. Whatever positive real number I give you, norm of this, I can view it as a non-zero complex number, and norm of this is itself, because it's positive real number. I'm getting back what I started with. In particular, all positive real numbers are in the image of this map. Therefore, image is the entire codomain. It's still surjective. Now, what is kernel of this map? An element belongs to the kernel if and only if its norm is 1. That happens precisely when it is on the unit circle centered at the origin. The unit circle centered at the origin, so that's the kernel, and that is denoted by S sub 1. That is what we use in order to show the unit circle centered at the origin. Again, because kernel is a subgroup, we immediately deduce that S1 under multiplication is definitely a subgroup of complex number, non-zero complex numbers and multiplication. So S1, the set of unit circle centered at origin under multiplication is a subgroup of non-zero complex numbers. Now let's look at the following group homomorphism. From real numbers under addition to the set of units, a unit circle. What is the map? We send real number x to e to power 2 pi I x. Remember this from complex numbers, we have that e to power I theta for every real number theta is cosine of theta plus I sine of theta for all theta that is real. So theta kind of give us the polar coordinates of the point cosine theta, sine theta. And e to power I theta is that rotation by angle theta. Now here I'm defining f by 2 pi times that. So it is 2 pi times I times x. It's easy, and you need to understand what exponential function is, but allowing if you're allowed to use basic properties of exponential functions, you can immediately check that it is a group homomorphism, because e to power 2 pi I x times e to power 2 pi I y is going to be e to power 2 pi I x plus y, and therefore f is a group homomorphism. And now we want to also understand its image and its kernel. Okay, so let's go through the details. If I give you two real numbers, f of x plus 1 is e to power 2 pi I x1 plus x2, but I can distribute this. I get that it's e to power 2 pi I x1 plus e to power 2 plus 2 pi I x2. But the basic properties of exponential function, I can split this plus and write it as multiplication. And that is f of x1 times f of x2. So f is indeed a group homomorphism because it preserves operations. So it sends a plus addition to dot. Now I want to understand image of this function. I pick something inside the codomain. I use the polar coordinates and think about it as cosine of theta I sine of theta. So if I use this polar coordinate shape, it's a unit circle, so this distance is 1. So z is, the components of z are essentially given by cosine and sine. So we get cosine of theta plus I sine theta. As I've mentioned, by Euler's formula, we have that this is nothing but e to power I theta. And therefore, this element, this z, can be viewed as f of theta over 2 pi, because f of theta over 2 pi is e to power 2 pi times this times I, and this 2 pi cancels out, and I get exactly what we wanted. So every element, every z in the unit circle, on the unit circle, is in the image of f. So image of f is again the entire codomain, and therefore f is surjective. Now, what is in the kernel? So x is in the kernel if and only if f of x is 1. That means e to power 2 pi ix is 1. If you think about it, this means what? This means I need to go back to this point. That means in the polar coordinates, the angle should be 0. Now, the angle being 0 means this 2 pi x is 0. No, not quite. It means that it can be every integer multiple of 2 pi. I need to end up landing to this point while rotating about this circle. And every integer multiple of 2 pi, I end up going to 1. So it is 1 if and only if 2 pi x is an integer multiple of 2 pi. But that means x is an integer. So x belongs to the kernel of f precisely when x is in the center. Therefore, kernel of f is just the set of integers. Now, let's finish this video by understanding centers or centralizers of some subgroups, some sub-elements or centers of the symmetric group and the dihedral group. Let's start by proving that center of the symmetric group S sub n, if n is at least 3, is trivial. Only identity can commute with all the permutations of S sub n of n elements if n is at least 3. Okay, that is what we want to show. We are going to proceed by a contradiction. Suppose to the contrary that I happen to find some non-identity element inside S sub n which is in the center of the symmetric group. That means sigma actually commutes with every element. And it's not identity, and therefore sigma of I is not going to be I for some integer I inside this interval. So sigma of I is something. It's something that is not I. Let's call it J. So I have two elements, these two distinguished elements. So these are I and J. I know I is sent to J. I don't know about the rest of the elements. I have no information about the rest of the elements. But I know that my function is a bijection, and I is sent to J, and I and J are not the same. From this, I want to deduce that there are two permutations that do not commute with this. There are some permutations that do not commute with this sigma. Because these I and J's they seem to be pretty important, and this n at least 3 is also important. I'm going to pick something that's not I and J. Remember, n is at least 3. So I can definitely find something inside the set that's neither I nor J. And I'm going to consider the permutation that sends I to K and sends K to I, but do not change other points. So I'm just switching I and K and asking myself, okay, what happens to this element? Can this commute with sigma? And the answer is no, it cannot. We'll check it. Let's check that. my claim is that, okay, of course, this is a permutation. I'm just switching the order of I and k. So it's a bijective map from 1 to 1 to itself. And my claim is that sigma and this tau do not commute. In order to show that these two permutations are not equal, it's enough to show that they do not give me the same value at a single point, and that point is going to be I. So I'm going to show that tau O sigma of I is different from sigma O tau of I. So that's my goal. I want to show that these are not equal. Let's see what this guy is. This is tau of j. J is neither I nor k. And therefore, tau is going to fix it, because tau is just switching I and k and does not touch the other points. It's going to fix the other points. In particular, j, which is neither I nor k, is going to be fixed by tau. Now, sigma of tau of I is what? It is sigma of k. My claim is that sigma of k cannot be j. Why is that the case? I want to say that this is different from this one. This is not equal to j. But what is j in terms of sigma? J is sigma of I. That's how we have it. I mean, that's how we defined it. So what we want to say is that sigma of k is not sigma of I, which is the case because sigma is a permutation and I is not k. I is not k, sigma is a permutation, it's bijective. Sigma of I cannot be sigma of k. That means sigma of I is j. J cannot be sigma of k. And that's exactly what we wanted to show by this equality, and this inequality. We deduce that tau of sigma of I is not sigma of tau. So they are not the same functions at I, and therefore they cannot be the same functions. That implies that sigma is not in the center of S sub n, which is a contradiction. That completes the proof. So again, pictorially, what we are doing, I'm taking these 3 points, I, j, and k, and then I'm following them up under sigma and tau. I know that when I follow I, under sigma, I go to j, and then under tau, I will be still in j. But when I apply tau, I send I to k. And I also notice that k is sent to I and I is sent to j under sigma. So this means that this k cannot go to the same point because the whole thing is supposed to be a bijection. It cannot go to the same point, so what we get from tau O sigma is going to be different from what we get from sigma or tau. Therefore, they are not equals. So this kind of a vector and pictorial understanding of permutations is quite important, quite useful, and we will come back to this later. So we understood center of a symmetric group. Now let's go to the dihedral group. Recall that a dihedral group, that means a group of symmetries of an n cycle, have 2 types of elements. Either rotations, so either I'm giving you this n cycle. So either I rotate 1 step, 2 steps, 3 steps, n steps. When I do it n steps, I go back to identity. Or I'm reflecting about one of these lines. So this line, that is what we call tau, or the half lines. So the line that passes through this point, or the line that passes through this point, or the line that passes through the next point, and so on. So we get n points. So if n is even, these lines are also diagonals. If n is odd, then they are not necessarily diagonals. But we get n lines of symmetries and these rotations. We discussed and proved that these are all the symmetries of these n cycle. I use the word rotation and reflection, but notice that here we started with this combinatorial object. This was an n cycle as a graph. We can identify it with a regular n-gon to visualize it, and then visualization can help us to use the words rotation and reflection. But the proof was completely combinatorial. We thought about these endpoints and their connectivity only as graphs. So we did not think about it in a Euclidean geometric sense. We did not use distance or angle. We just use connectivity, whether or not a vertex is connected to another one. That's just a remark. And we use that combinatorial structure to show that all the symmetries of this combinatorial graph consists of these 2n transformations. When we label the vertices by elements of z sub n, these transformations, this permutation, this rotation can be viewed as a shift by 1, and this reflection can be viewed by sending x to its additive inverse. Having this sigma and tau, we could list, and we did list, all the elements of the symmetries of this n cycle, and they are of this form. N of them are rotations, and this n minus 1 of them, and this n of them are reflections. Okay, if I interpret them in terms of Euclidean geometry. And we notice that sigma to the I is nothing but I step shift, and sigma to the I is identity precisely when this I step shift is the same as 0 shift, which means that n is a multiple, I is a multiple of n. And tau squared is identity, because tau of negative x is negative of negative x, which is x. Therefore, tau squared is the identity map. Now, what is crucial, and it's interesting and it's important to know, is that when I multiply tau by, okay, what am I doing? So I have the list of elements. I want to kind of understand multiplication of these elements. So among these ones are clear how we multiply. Now, among these ones, if I understand how to multiply this one by this one, then maybe I can understand how to multiply it by the other ones. That's kind of what I'm doing over here. I'm multiplying tau by this one. But remember, tau inverse is simply tau. So that's why I'm conjugating by sigma to the I by tau, and I'm trying to understand what it gives me. Tau inverse is simply tau, as we have just pointed out. So tau inverse is just tau. I get tau of x is negative x. Sigma to power I of this is I step shift. And tau of this is negative of this one, which means x plus negative of I. And that is negative I step shift of x. It means sigma to the power negative I. So it's quite interesting, because when I conjugate by tau, I'm just negating the power. This is special for dihedral group, quite special for dihedral group. So we have this equality that tau O sigma to the I O tau inverse, or simply tau, is sigma to power negative I. This is a special property of dihedral groups. Knowing this, you can write down the entire matrix, the entire multiplication table for this group. You can list all the elements and try to understand what the multiplication table looks like for some specific n as a good exercise. I would suggest that you do it, let's say for n equals to 3, and try to find out what kind of multiplication table you end up getting. In the video that you see for the office hour, I've done it without this nice way of using sigma and tau, and I did it by hand, and there I did it for S sub 3, but you can see that S sub 3 is in fact the same as D sub 6, where I have a cycle, 3 cycle, and I want to understand symmetries of 3 cycles. That would be every permutation of 1, 2, and 3, because it's a complete graph as well. Anyway, so I urge you to use this method to understand the multiplication table of D sub 6. Okay. Having this multiplication understanding in the dihedral group, I want to show the next proposition. It tells us, and we could guess as well, as I've indicated, the difference between these reflections when n is odd or even geometrically. When n is even, these reflections are coming from reflections about the diagonals. When n is odd, they are not diagonals. We could guess that there should be a difference between these two cases, and we see it in the next proposition algebraically. If n is odd, then centralizer of the reflection tau has only 2 elements. One of them is identity and the other one is tau. When n is even, however, we have 4 elements in the centralizer of tau. Of course, one of them is identity and the other one is tau, but we also have a central reflection about the origin. I can negate everything because n is even. I do have this central reflection. When n is odd, I don't have this central reflection. So if I use this center and I reflect everything, I don't get the original triangle. I end up getting this triangle. But when it is even, let's say I pick a hexagon, then this one does have a central reflection, and that is precisely 180 rotation. That's sigma to power n half. So 180 rotation, then this comes over here, this comes over here, and this one comes to this point. So I have this central reflection that can be also viewed as a 180 rotation. That is sigma to power n half. And therefore sigma to power n half composed with tau is also a reflection. Which commutes with tau. So when n is even, I have 4 elements inside the centralizer of tau, and when n is odd, I have only 2 elements. Okay, let's see why this is the case. Let's start with a case that n is odd. But okay, before that, let's point out that every element is in the centralizer of that element, and identity is also inside that. So definitely these 2 elements are in the centralizer. Now let's look at this equality that we have over here. From here, we can deduce that if sigma to the I commutes with tau, if sigma to the I is in the centralizer of tau, then this is supposed to be like sigma to the I. It's equal to the sigma to the I. But at the same time, we did this computation, we realized that it is sigma to power negative I. So sigma to the I needs to be, so if sigma to the I is in the centralizer, then I have this equality. And therefore, by that equation, we get that sigma to power negative I is supposed to be sigma to the I, which means if I multiply both sides by sigma to power I, we get that sigma to power 2I is supposed to be identity. But here we argued the power of sigma is identity precisely when that power is a multiple of n. So, excuse me. Sorry for that. So sigma to power 2I is identity precisely when the power 2I is a multiple of n. Now, if n is odd, then using Euclid's, so n is odd, these two are coprime, using Euclid's lemma, we deduce that n divides I, therefore sigma to the I is identity. So the only power of sigma to the I that commutes with tau would be the identity. When n is even, however, that's different. So if n is odd, I have that this is dividing to I, n and 2 are coprime, therefore n divides I, which means sigma to the I is identity. So what we discussed shows that if n is odd, the only element among this set that can be inside the centralizer of tau is the identity. Now, if n is even, then n divides 2I implies that n half divides I, and vice versa. If n half divides I, then twice both sides, n divides 2I. So altogether, we see that this equality happens precisely when I is a multiple of n half. So if n is even, the only elements, and precisely those elements that are inside this set and are in the centralizer of tau, are those powers of sigma to the I that where the power is a multiple of I, is a multiple of n half. There are only two integers that are multiples of n half and live in the range from 0 to n minus 1. One of them is 0, the other one is n half. So this intersection has precisely two elements. One of them is identity, the other one is this central reflection, this 180 rotation, sigma to power n half. Okay, now, so far we understood intersection of the centralizer with the first rotation, with a set of rotations. How about reflections? We notice that because tau is in the centralizer, we immediately get that sigma to the I O tau is in the centralizer. If and only if when I multiply by tau, I can get rid of this. If this is inside the centralizer, this is a subgroup. Tau belongs to this subgroup. So I can multiply by tau inverse, and it should be still inside this group. When I multiply by tau inverse, I end up getting sigma to the I. So if this guy belongs to this subgroup, so does sigma to the I, because because here I pointed out, because tau is inside this subgroup. Now, if sigma to the I is inside this subgroup, because tau is also inside this subgroup, I can multiply them. I deduce this. So this is if and only if sigma to the I O tau is inside the centralizer, if and only if sigma to the I is inside the centralizer. We have already discussed what kind of sigma to the i's are inside the centralizer. If n is odd, only identity. If n is even, only these guys. So now all these three together imply that when in n is odd, centralizer has only two elements, identity coming from the intersection by this, and then I can multiply it by tau. Oops, what happens? Or when n is even, then I have four elements. This comes from intersection by powers of sigma. Then I can multiply them by tau, and I get these four elements inside this centralizer. So altogether, we understood centralizer of tau. Now let's try to understand center of the dihedral group, and that would be the last example that we have for this in this video. When n is odd and at least one, we are going to show that the dihedral group has only identity inside its center. But when n is even and at least two, strictly more than two, sorry for that, otherwise we don't have this kind of polygon shape, then the center of this dihedral group consists of two elements. One of them is, of course, identity, and the other one is this 180 rotation, central reflection of my shape. The central reflection actually commutes with all other symmetries. Okay, so let's prove this. And of course, center means all the elements, all the symmetries that commute with every other symmetry. So if something is in the center, then it's supposed to commute with tau in particular. So center of d sub 2n is definitely a subgroup of the centralizer of tau, centralizer of every element, in particular tau. In the previous theorem, we understood centralizer of tau. In particular, when n is odd, from this we deduce that center is either identity or tau. But notice, it cannot have tau in it. Why is that the case? So let's see, I have it over here. Again, center, by the previous proposition and the fact that it is a subset of centralizer of tau, it contains identity and tau at most. If we show it cannot contain tau, then we are done. It's just identity. But let's suppose to the contrary that it does contain tau, and then we are going to get a contradiction out of it. If tau is in the center, what does that mean? This means tau commutes with every element of the group. That means centralizer of tau is the entire group. That's in fact if and only if. For an arbitrary group G, an element G belongs to the center if and only if centralizer of this element is what? Think about it. G is in the center. It means G should commute with every element inside the group. So every element should be in the centralizer. So that's if and only if. Now, if tau was in the center, then the centralizer was supposed to be the entire group. But that's not possible because centralizer of tau, in this case, has two elements. But the entire group has two n elements. But n is more than one. That's not possible. So from here we get this, which is a contradiction. And therefore, tau is not in the center. Center was a subset of the centralizer. And in this, we have only identity and tau. Tau is not in the center, so that means center is only identity. Okay, so that shows the odd case. Now let's see what happens when n is even. When n is even, I want to discuss that in fact 180 rotation is in the center of this of the dihedral group. So I'm going to check first that it commutes with all the rotations, and that's rather easy because every rotation is a power of sigma. So we get that it is sigma to power n half plus I, but now I can flip this, and I can write it as I plus n half, which is sigma to the I of sigma to power n half. Therefore, this sigma to power n half commutes with sigma to the I for every integer I. Now let's see why it commutes with sigma to the I o tau. These are all the rest of the elements inside the dihedral group. We know that this commutes with sigma to the I. We know that it commutes with tau. That's enough, because then we deduce that both of them are in the centralizer of sigma to power n half. But let's do it one step at a time as well. So these two commute with each other, so I can write it like this. And these two commute with each other, as we proved. This belongs to the centralizer, so it commutes with this. And altogether, we get the desired result. So sigma to power n half is indeed in the center of the dihedral group, because every element of the dihedral group is either of this form or of this form. So identity and sigma to power n half, both of them are in the center of the dihedral group. Next, I want to show that they are the only ones. But notice that centralizer of tau has 4 elements. And that's not the entire dihedral group. That means tau is not in the center. Remember again, if tau was in the center, then centralizer of tau was supposed to be the entire group. But it's not the entire group, which implies that tau is not in the center. Center is a subset of the subgroup of this, is a subgroup of this, and it is a subset of the centralizer of tau. A centralizer of tau has 4 elements. So center of this definitely contains identity and sigma to the power n half. It does not contain tau. How about this one? Can it contain this one? If it contains this, because it also contains this, I can cancel it out. I can cancel these guys. I deduce that tau should be inside it, and that would be a contradiction. This is what I have over here. Because this is a subgroup, and sigma to power n half is here, tau is not here, their product cannot be here. Because if the product was here, then I can cancel it out and deduce that tau is here. So their product is not here, the composite is not here. So this is not in the center, this is not in the center, this is in the center, this is in the center, and these are the only possible elements that can be in the center. So altogether, we get the desired equality. So altogether, we have that the center of the dihedral group is trivial if n is odd, and the center of the dihedral group d sub 2n is contains 2 elements, precisely 2 elements, identity and 180 rotation, if and only if n is even. Okay, so we'll continue with understanding of some particular results about homomorphisms and subgroups in the next video. Let's stop for now.